So in this video, I want to talk about molecular orbitals that are formed by elements in the second period. So you want to go back, if you haven't looked at the previous video, you want to have all these concepts in mind. Okay, energy diagram, the MO energy diagram. You want to have a firm concept on calculating bond order, how to draw the energy diagram, how to fill out the electrons, and how to count valence electrons for molecules. Okay, and then how to determine whether a molecule is stable or not. Now we're going to go to second period elements. Now, in the second period elements, the first two elements in the second period, which is lithium and beryllium, actually has a very similar type of molecular orbital as the first period element. What that means is that they have only two molecular orbital in the ground state, and that's the sigma. Instead of 1s, there's sigma 2s and sigma 2s star. Okay? And the reason for this is if you think about both of these elements, their valence electron lies in the 2s orbital, right? So in other words, the lithium atom has 1 electron in the 2s orbital, and the beryllium atom has 2 electrons in the 2s orbital, and these are both the valence electrons. So when you're trying to do the linear combination, you only need to worry about the valence electron because they're the ones that are most likely to react with other electrons because they're outermost. So as a result, when we try to create molecular orbitals for these guys, we would write them as sigma 2s and sigma 2s star. It doesn't mean that at the bottom there's no sigma 1s, but those don't really play a role in terms of the properties of the molecule. Okay? You can then predict certain properties associated with these molecules that are formed by these elements, lithium and beryllium. So for example, if I want to know if lithium, let's say lithium 2, whether lithium 2 exists or not, I can do the same things that I've been doing for the first period elements. I can just calculate first off the number of valence electrons. So lithium 2, what is the number of valence electron? Okay. Now you want to be a little careful here. A lot of you might make a mistake, but there's 2 valence electron. Okay, why 2? Remember that lithium is in group 1A, so each lithium is just 1 electron, right? Because it's group 1A. So if it's group 1A, it's always just 1 valence electron. Okay. So in this case, because you have lithium 2, then you have 2 valence electron. That's it. You don't have 6 valence electron. You want to be careful. 6 is the number of total electrons, but only 2 of them are valence. The other 4 are core electrons. Okay? All right. So if I want to calculate, if I want to fill out the energy diagram, I have 2 electrons, so I'm going to put them right here, which means that my bond order, which is what I need to do to calculate whether a molecule exists or not, would be 2 number of electrons in the bonding orbital minus 0 number of electrons in the antibonding, which is the sigma 2s star, divided by 2, so then it's 1.0. Okay, so that tells me that this molecule does exist, Li2. Okay, let's go to Be2. What about Be2? This is still sigma 2s and sigma 2s star. Does it exist? Well, go ahead and first figure out the number of valence. What is the number of valence electron? Beryllium is group 2A, so that means each beryllium has 2 valence electron. Now you have 2 of them, so it's 4 valence electron total. You put those electrons in these configuration. You get this, and then the bond order, of course, is 2 minus 2 over 2, which is 0. So in other words, beryllium 2 is predicted not to exist by molecular orbital theory. Okay? So that's how you would do it for lithium and beryllium. Now we're going to move on to the rest of the second period. There's a little bit of complication with the rest of the second period. If you start to go to the rest of the second period, which starts with boron and then carbon, nitrogen, oxygen, and fluorine, and we're going to skip neon because neon doesn't form any compounds. What you see is the following. You see that all of these guys, the unique thing is they have valence electron in both 2s and 2p orbitals. So in other words, if I want to create molecular orbitals, I have to do linear combination of 2s orbitals. I also have to do linear combinations of 2p orbitals. So there's 2 types of molecular orbitals you can form. Okay. For 2s orbital, we already know. When you do your linear combination, I'm just going to write it as LC here. You get your sigma 2s and sigma 2s star. Okay? Now, what happens to if you were to do the p molecular orbital when you're trying to do a linear combination? Let me talk about it in the next slide, and then we'll come back here again. Notice that what's unique about the p orbital, as we've discussed before in valence bond theory, is that there are three different ways p orbitals are arranged, right? You have the 2px, which is aligned on the x-axis. You have 2py and 2pz. And notice what happens is that you also, just to remind you again of p orbitals, they also have these positive and negative phase. So you can see here, maybe it's a little hard to see, but this one says positive symbol inside that lobe, and this one has a little negative symbol inside the lobe, and so is with the other lobes of the p orbital. Okay. Now it turns out that you get different types of molecular orbital depending on which p orbitals are being combined. If you combine the p orbitals that are aligned like this, you get this type of molecular orbital, which we call the sigma molecular orbital. That's the same type of sigma that we use for the s orbital. Okay, and then if you use the other two p orbitals and you do linear combination with them, you get a different type of p orbital called the pi molecular orbital. Okay, so what's the difference between these two? As we indicated with valence bond theory, the sigma just means that the molecular orbital that you get is cylindrically symmetric around the internuclear axis, okay, or the bond axis. If you do an across here, you'll see that the shape are exactly symmetric around the bond axis. Whereas these guys, turns out that they're not symmetric around the bond axis. In fact, there's usually a node around the bond axis, and then it's symmetric actually around the axis that's perpendicular to the bond axis, which is this vertical axis right here. Okay, let's take a look a little bit more into the shape of these molecular orbitals. So this is an illustration of how the sigma molecular orbital from the 2p linear combination is obtained. So remember that the way you do this is you just add them like you add waves, right? So in other words, you're going to add these two p orbitals, but in one way you're going to add them as constructive interference, and the other way you're going to add them as destructive interference. Okay, so it turns out that if you add them, you get these two molecular orbital. One looks like this, and the other one looks like that. And the different color here, let me just kind of indicate there. The different color here, blue and yellow, just indicates the phases. So remember that p orbital can be either positive or negative, as I said here. One lobe is positive, the other one is negative. So this is really what that means. That's showing that one side is positive and the other one is negative. Okay. But what's unique about this orbital is that you have a lot of electron density in between the two nuclei, right? So the nuclei are right there, and then you can see that there's a lot of electron density in between them, which means that this is what we refer to as the bonding molecular orbital, because it's a bonding molecular orbital. We'll give it the symbol sigma, because remember this is the sigma one, sigma 2p, because it comes from adding two 2p orbitals. This one, on the other hand, you can see that the electron density is more associated with each nucleus as opposed to distributed between the two of them. So this is the anti-bonding molecular orbital, so we call it sigma 2p star molecular orbital. Okay. Right now, let's think about why they're called sigma. Remember what I said earlier about sigma. Sigma just means that they're cylindrically symmetric around the bond axis, which means that if I were to draw the bond axis, which is the axis just running through the two nuclei, when I rotate from top to bottom, if I were to rotate like this, okay, then the top part and the bottom part will be symmetric, will be identical. And you can see that that's the case here, because the blue part is going to rotate into the blue part at the bottom, the yellow part is going to rotate into the yellow part at the bottom, and the shape is exactly identical. And you can look at this one as well. The same thing is true, because you have the blue one rotating into the blue one. So the sigma component is true, it's just that one of them is bonding, and the other one is anti-bonding. Okay? All right. Now let's talk about the other two p orbitals, right? These guys right here, okay? When you add these two together, whether constructively or destructively, you don't get this cylindrically symmetric shape anymore. You get something else. So this is the result of adding those two orbitals from the 2p, the other two 2p orbitals that you have, okay? The one that's shown right here with the, here I'm going to circle them again, these guys right here, okay? what you get is that if you were to add these two guys, for example, what you get is a shape that looks like this, okay? And if you were to add it, that's if you were to do it constructive interference. If you do destructive interference, then you get something that looks like that, okay? But one thing I want to point out is that if you were to draw the internuclear axis, which is this line right here, you'll see that the top part and the bottom part is not symmetric when you rotate, okay? Here is yellow and here is blue, and remember those are representing phases. So one side is positive, the other one is negative, so they're not symmetric. But it is symmetric around which axis? It's symmetric around this axis, right? So if I were to rotate it this way, then the yellow goes to yellow and then the blue goes to blue as well. So they're symmetric around that axis, but not around the internuclear axis, okay? So in other words, we can't call them sigma orbitals anymore, sigma molecular orbitals. We have to call them something else, and we call them pi molecular orbitals. Now, depending on what they come from, there's two different pi molecular orbitals we can get. If we add the px atomic orbitals, we get these guys. If we add the py atomic orbitals, we get these guys. They're really just 90 degrees away from these guys, so it's sort of like you're rotating. You can see that the blue now is at the back, so if you were to rotate it this way, then the yellow one becomes in front of you, and then the blue becomes to the back side of the paper, right? So that's really just what happens. It's just a rotation of those guys. Same thing right here, okay? But what you get is you get these pi 2p orbitals, and you get two of them that are bonding, and you get two pi 2p star orbital, okay? So in total, for the second period elements, these are the orbitals you're going to get. You get sigma 2s star, that's from the 2s orbital, and then you get sigma 2p star, and then you get pi 2p and pi 2p star from 1, and then you get another one, so there's two of each of these guys, two of these, and then two of these as well. Okay, so in total you're going to have 1, 2, 3, 4, 5, 6, 7, 8 total molecular orbitals. Okay, in the next video we will talk about how the energy of this orbital are arranged, and that turns out to depend a lot on the type of elements you have.